All right, let's try this one more time. So, moving on. Applications of growth and decay. So, we've done this topic before in other math classes, and I'm sure you did it in chemistry and in biology. So, we're gonna take a slightly different approach with these problems. Now that we have a formal growth and decay model that we are going to use all the time, we work on the assumption that the rate of decay is proportional to the amount of the material. So an example is the following. Given this information, the half-lives of some of the common radioactive isotopes is what you see here. Radioactivity in Chernobyl, USSR. Here's the application part. Suppose that 15 grams of cesium isotope 137 that was released during the 1986 Chernobyl nuclear accident and absorbed into the groundwater. How long will it take for 15 grams to decay to 1 gram and become safer to drink? So again, with this example, you have to recognize that this is a half-life problem. It is going to be a exponential growth or decay model. So we're going to identify it as A of t, right? Instead of y, just because it is a story problem. So we're going to call it A of t is equal to C e k to the t. So this is the equation that we're going to use. Now, they gave us two pieces of information that when time is 0, you have 15 grams of cesium-137. And we're going to use this to solve for C. Just like we did in the last example. So once you set this up, you got your 15. This is the amount with respect to time. You plug this in, and you see that C is equal to 15. And just like we said at the beginning of these notes, right? C is the initial value. So anytime they give you a value at t equals 0, that will be your C. So far, we have that A of t is equal to 15 e to the kt. Now, what values are we going to use for to solve for K? So given this information up here for cesium, cesium's half-life is 30 years. So when T is 30, right, 30 years, half of the material is going to be gone. So we're going to have 7.5 grams of cesium in the drinking water. So we're going to, just like before, we got 7.5 is equal to the 15e to the k times 30. And we're going to solve this. And it's always going to be the same thing, correct? So you're going to divide both sides by 15. So you end up with a half is equal to a to the k to the 30k. You're going to take the ln of both sides. So you have ln of 1/2 is equal to 30k. And you're going to divide both sides by 30. So k is going to be equal to 1 over 30 and then ln of 1 over 2. Now when you simplify this, right, the ln of 1 divided by 2, that's the same thing as saying ln of 1 minus ln of 2. So 1 over 30 and then ln of 1 minus ln of 2. And the reason why this is important is because we know that ln of 1 is just 0. So k is going to be equivalent to negative ln of 2 over 30. That's going to be our easier value. So now we have our equation. We have a of t, or our particular solution, right? We have a of t is equal to 15 e, and then k is now known as negative ln of 2 over 30. You can keep it as ln of 1/2, all right, times 1 over 30 times t. So here's our equation. Now the question is how long, right? Or what is t? So t question mark, when a of t is 15 grams. So now that you have your equation, what's left is to set your a of t equal to 1, ln of 2 divided by 30, and you're going to solve for t. So divide both sides by 15, right? Take the ln of both sides. So we got 1 over 15. I'm going to take the ln of both sides right off the bat, because when we take the ln of this side after I divide by 15, you're left with what are you left with? Probably should have cleaned this up just a little bit more to help us out. Yeah, let's do that. All right, before we even work this out, let's clean this up just a little bit more, right? Now with a calculator, not necessary to clean this up any more than you have to. So let's do this. We got our 1 equals, let's divide both sides by 15 first. So we got e to the negative ln of 2 over 30 times t. How could we clean this up a little bit more? Well, using the logs, wow, okay, this is not really that easy to recognize right here. But if we had 1 over 15 is equal to e, and then we got the t over 30 negative of ln of 2, because this is in front, we can rewrite that as 1 over 15 equals e to the negative ln of 2 raised to the t over 30. And the reason why that is so nice is because, well, let's put the negative up here too with it. And the reason that that is nice is because this e and this ln will now cancel out before we even take the ln of both sides. And that whole thing will come down to be t to the negative 2 over 30. Which is the same thing as saying 1 over 15 equals 1 over 2 to the t over 30. So now when we solve for t, we got to bring this out from the denominator first. Probably should have left this as ln of 1/2, but it's okay. So multiply both sides by t over 30, 2 to the t over 30. And multiply both sides by 15. So we got t, 2t over 30 is equal to 15. Now we can take the ln of both sides. So we got t over 30 is equal to ln of 15 times 30 times 30. And you have ln of 15 times 30 is equal to t. Now when you multiply this, ln of 15 times 30, you should get 117 years. Please someone check that. Check my math. That should be the answer. 117.207 years. All right. And if I got that answer wrong, we will double check my math tomorrow. All right, example 3, you've got your fruit fly population. I'm going to let you guys work on this one. So they do give you, this is not going to be a half-life number, but an absent-minded graduate student at the university studying the population of fruit flies. She works under a promise that this experiment population of fruit flies increases according to the law of exponential growth. She counts 100 fruit flies after the second day. So we know that when t is equal to 2, you got 100 fruit flies of the experiment, and 300 fruit flies on the 4th day. So when t is equal to 4, you got 300 fruit flies. Now, this one is a little bit harder because the two values that you have, neither one of them will eliminate c. So we're going to use both values to solve an equation and then set those things equal to each other. So, however, she forgot to record the number of fruit flies she initially had, so when t equals 0, approximately how many fruit flies were in the original population. So the question is, when t equals 0, what is f of t? So in order to do this, we have to use the information that we know. Well, first of all, we know that the function that we're using is the same. So the first thing we're going to do is we have 100 equals C e to the k times 2, but we also have 300 is equal to C e to the k times 4. Neither one of these is going to eliminate e. So right now, we have two equations that we can use algebraically by solving both of them for c and then setting those equal to each other. So in this equation, c is equal to 100 divided by e to the 2k. And in this equation, c is equal to 300 divided by e to the 4k. So since I have two equations that are within the same pieces of from the same information, I can take the two c's and set them equal to each other. Now what this will allow me to do is actually solve for k first. So once you solve for k, so go ahead and do that, you should end up with an equation for k. And once you get that equation, all you have to do, and once you solve it, you still don't know what c is, right? But we want to know what is the initial population. So the question is, what is f of t when t equals 0? Well, when t equals 0, f of t is going to be equivalent to c. So you're solving for c. So I'm going to give you guys what k is right here. That is your k. And then you just got to plug in 0 here. And once you plug in 0 for t, that will give you your c value. So finish up that problem and let's keep going. Last example, 4 months after it stops advertising, a manufacturing company noticed that its sales have dropped from 100,000 units per month to 80,000 units per month. If the sales follow an exponential pattern of decline, what will they be to the nearest unit after 2 months? So the 100,000 units, that is the initial reading. Okay? And when did the 80,000 happen? Well, it says right here. At 4 months, they were selling 80,000 units per month. So this one will help you solve for C, and then this guy will help you solve for K. And once you solve, you're going to plug in a value for T. If the sale follows an exponential decline, what will they be to the nearest after another 2 months? So what is T? Is T 2 or is T 6? Okay, so that's something you have to be careful. Determine which one's the correct one and finish up that example. So Newton's law of cooling states that the rate of change in a temperature of an object is proportional to the difference between the object's temperature and the temperature of the surrounding medium. They actually use Newton's law of cooling to determine time of death for people, using the temperature of the room that they are in and the temperature of their body at that time. So this is the equation. K is going to be proportional, or the average rate of change in the temperature is proportional to the temperature of the object minus the temperature of the surrounding environment. So the temperature of the body and take away the temperature of the environment that they are in. So Newton's law of cooling isn't specifically tested on the AP exam, although models that closely resemble its form are sometimes tested. If they do ask you a question about it, they will be giving you the equation. You won't have to memorize it. I'm going to leave you with example 5 just because of the time of the video. If you need to use the QR code to help you finish up that problem, you go ahead. Make sure that you identify the correct t values. All right. Now remember, this is a differential equation, and this is with respect to time. So when you separate to integrate this guy, you're going to have 1 over t of 0 minus te is, and that goes with dt of 0 equals k times dt. So here's it separate, and then you can integrate, but there are going to be some values that are in there that are constant. The constant value is going to be the temperature in the surrounding environment. That should not be changing, okay? Just like the heat in your house. If you are cold or hot, but your heat is constant, then it's your body temperature that is changing. All right, and then we're going to leave example 6 as bell work for class tomorrow. All right, enjoy.